Test. Okay. Hey, everyone. I hope you were able to enjoy your lunch and Gabi's talk. We're now going to go ahead with the advanced track. And so Armando from Well-Typed is going to talk about IOSim. Please take it away.
Thank you. Thank you very much, Jasper. Okay. So this sort of should be more like a workshop discussion type of presentation. So feel free to interrupt me with questions. I have a mic here, but if it's like some emergent question that I didn't explain something correctly, or you want me to go over into more details, just try to speak a little bit louder. I think it should be fine. But yeah, otherwise, I have the slide just to guide me through the presentation. It can take as long as we wish, so this ought to be like the two halves with a pause in between. The first set of slides is me just going over IOSim very high level and some of the stuff needed for you to work with IOSim. Then we'll probably have a brief demo where I'll show you it in action, and then I have some small project that hopefully you can try for yourselves, and me and Duncan over there will go over the room and probably answer your questions or issues with the library. Yeah, let's start. So about me, my name is Armando. I'm working at Well-Typed, and I'm on the project with the IOHK team, networking team, which is also the team that developed this great tool, the IO simulator. So shout out to Duncan, Marcin, and Carl. I hope those are the main three ones. And I'm enthusiastic about formal methods and distributed systems, and IOSim is great to work with both of these areas. You can find me on those two social media. Yeah, so you can find the slides and the code for the materials here. Just go over to the Well-Typed GitHub organization, and they'll be there. Okay, so what's IO Simulator? So it's a library that can be a drop-in replacement for IO in Haskell. So you have IO where everything runs in real world, right? Then IOSim is kind of the same thing, but it allows you to run a deterministically program with access to the trace event of that program. And I'll show you more about it later. So IOSim, when I say IOSim, I actually mean IOSim and IO classes, which are the two libraries that go hand in hand. More on that later. And as it says there, it's a tool and a framework to analyze simulated execution traces. So you can see how that can work. So we use it at IOHK, and probably soon to be in someone's personal project after this talk. And how? So we use IOSim to run the exactly same code, either in production or in simulation. We also use it to run tests with. We simulate high and low level components from the Ouroboros network stack. So everything from high level components that make everything work down to the message passing and networking protocols. So we can find edge case bugs. For example, in the case of networking, you have this very rare phenomenon, which is the simultaneous open of TCP. And that can be a tricky edge case, and IOSim can be useful for you to make sure you cover that with no issues. And also for the distributed systems part, instead of running your code in an AWS instance for like 1 week and see if it crashed, and then look at the logs and wait a really long time to see if it's good to production, we can just fire up a simulation with years worth of virtual time to kind of gain more confidence about the code we're going to deploy. Or any other crazy use case you might find for this. We recently published this on GitHub. It's not yet on Hackage, so the repository that I linked in the previous slide already has all the boilerplate. It should be just cabal build and cabal run for everything to work. But yeah, hopefully we'll get that to Hackage soon enough. So this is the official repository for the IOSim and IO classes libraries. It's over at the Input-Output HK organization. So feel free to tinker around it during the presentation and look for questions to ask. So as I said about this workshop, hopefully we'll get a project up and running. In the link there's a link for my GitHub repository. We're going to do a brief introduction to contravariant logging and more on why I'm going to talk about logging when time is due. Then a brief high-level explanation of how IOSim works, and maybe their internals if someone is interested. And look how we can test stuff with this simulation framework. And then if we have time, put everything together in a small project, and then me and Duncan will probably help you through that. And if there's no time, I have a proposed solution, and I can walk over it and show you how it could look like. OK, so why logging? There are plenty of nice tutorials about contravariant logging. You might be familiar with a lot of those. We're just going to go over the basics and some of motivation and context for this. So other reasons you might be familiar with logging already. Logging is useful for you to inject code into your code base and get some idea of what the code is doing during execution, right? There are a couple issues with that, like you're tainting your implementation business code with logging stuff. You might want like severity levels or printing to an EKG sort of live parameters overview of everything, and you just specialize too much in your business code, probably too early in that sense. So contravariant logging is simple enough that you can just build as you need to, specialize more your logging frameworks, and then instantiate to any logging library that you're more familiar with. With IOSim is useful because you get the best of both worlds. You get the tracing, getting to know how everything is working while your code is executing. And with IOSim, you can get all that information in your simulated trace. So you can execute it and hopefully write properties with. So yeah, logging will give us a way to build events we care about into the trace. So this is the type signature. So contravariant, I understand I didn't explain it correctly. So contravariant is like functor, but you transform the inputs, while in functors you transform the output, right? So this is nice because you can, with a trace of a given type, you can either lift that type into a bigger trace or specialize that trace into something like, for example, if you have a data type that has a name in it, you can, if you have a trace for that big data type, you can just contramap and project the name, and you get a trace for the name. And yeah, so we're going to work with ContraTracer, which is a small library that we use at IOHK. These are the main types and type class instances, and that trace width is exactly what we're going to see in the code to get the logging working and printing into the simulation trace. So yeah, so just some examples. Null tracer doesn't print anything. Standard out tracer prints a put string ln. This is in IO, obviously. With IOSim, you're going to have trace m. You don't have to understand what the implementation is, but you just have to know that that's the thing you want to use when running a IOSim program. OK. So everything all right until now? No questions whatsoever? Good. OK. So IOSim is the library that supports the asynchronous exception. Oh, yeah. So IOSim offers a very extensive subset of I/O. As you can see here, it supports synchronous exceptions, concurrency, fork I/O or async-based APIs, as you're familiar, the timeout API, STM, everything you might want in an I/O program. That's why it's very nice to use with as a drop-in replacement for I/O. And so IOSim offers the IOSim data type, functions to manipulate the traces I show you, and this funny thing, IOSim POR, that stands for partial order reduction, because the way IOSim works, it just simulates one possible trace execution of your program. So if you have different threads, you could have different interleavings, for example, that could lead to different race conditions and whatnot. So you might have tests passing just because the universe deemed that that was the scheduling that IOSim was going to run. But if it by any chance would pick a different one, maybe you would have a deadlock or something like that. So IOSim POR is tries to find different interleaves that can lead to problematic counterexamples for your tests. I'm not going to cover this into a lot of detail, but it's nice to know that the IOSim library has this cool thing. So IO classes is a library. So the way you transform IO code into IOSim code is you abstract over the IO monad with an M parameter, for example. And IO classes offers you all the type classes for the capabilities that you might want. So you have monad async for everything related to concurrency and the async API that you might be familiar with. Event log, fork, STM is right there. Time and timer for time. So these are stuff that you're going to see when working in the small project. Okay, so quick example. We have a trace data type, trace example, and an example code written for I/O. So the way we're going to use tracing is we're going to pass the tracer as an argument here, and the program is really simple. So we just want to do some thread delay, wait 1,000 microseconds or seconds. I'm not sure. Never sure which one is it. And then we just want to print something to the screen, right? And we could do tracing with put string line, right? But we're trying to be more civilized and use trace with here. We write a bunch of data constructors for each event we care about. And then whenever we're going to do thread delay, we trace with setting thread delay to 1,000. And whenever we're going to print something, we're going to trace that event as well. So, and here's the code written in IOSim. So you can see that I/O is no longer explicit here. We have monad delay and monad say constraints. And really the only thing that changes here is the say, because put string line is specialized to I/O. So here is just to highlight one good use case of IOSim. So if you don't want it to use for anything fancy, like we were doing with concurrence distributed systems and that sort of complex architectures, if you have just a plain I/O program and you thought it should be working and it's not, if you just want to inspect what is going on there, you can just rewrite your program in I/O classes in IOSim and then run the trace and inspect it and see if your reasoning about this program is correct. So remember this program, we are tracing, set thread delay to 1,000, then we're doing thread delay, and then we're tracing again and just printing something to the screen. This is what you would see if you run the simulation and ask for the trace of it. So let's just go over very briefly through each event. So the first one, notice the time. So the time changes because we have a thread delay. So at time 0, you can expect those events to be happening all at the same time, but through that order of events. Okay? So the first one is an event log message that says that we're tracing something. Excuse me, tracing something. In this case, it's event say. Then an event timer is created with an ID of 0. So this is the thread delay line here. So thread delay is putting a timer that is going to fire at 1,000 seconds. Then we have a transaction blocked on tvar ID 0, which should be the tvar for the timeout in register delay style, if you're familiar. And then the main, yeah? Thank you.
It's just a small thing, really.
Can you say exactly what I have to do to go from the program in the previous slide to get to this output?
Sure, I don't think I have it in the slide, but it should just be, so you have runSim or throw. These are the functions that the API offers for you to run a simulation. So you can either get the whole result in the program that we saw, it would be just unit. But if by any chance your program would return an integer or any other type, you'd get it from runSim. But if you run simtrace, you'll get a trace out of it. You can even get a more detailed trace with trace events, like with the time, thread IDs, and labels and whatnot. So you just run simtrace of this example IOSim program, run it in a main function or something like that, and you would see this printed on the screen. And I have a demo that...
Okay, thank you. And I guess there's also a way to still run it as normal I.O., right?
Yeah, so the way to run it as normal I.O. is running it in a main that has a type signature I.O., and then I.O. classes have as the definitions for I.O. in it.
Okay, thank you very much.
For each class.
Any
Thank
other
you,
questions
Andres.
by chance at this point?
Okay.
So what is the performance cost of using IOSim instead of just I.O.?
Okay, thank you for the question. So the performance cost obviously is going to be slower than I.O., right?
You mean if you run it in I.O., or the performance cost if you run it in the simulation?
I mean, if you write your program using IOSim instead of I.O., once you want to run it on a real-life example, is there a performance cost?
There's a performance cost of simulating stuff, so there's a lot going on in between to simulate and get the semantics of each. For example, if you're using STM and TVARs and whatnot, it's all simulated, so it runs a overhead on that. Obviously, I.O. would be quicker. Yeah.
Or perhaps I should just listen rather than trying.
I'm not sure if you were asking this question, but a question that you might have meant was, if you use the IOSim classes and you want to run it in I.O., i.e. for real,
I see.
Is that slower? And the answer is it should be the same. At least it should be the same if you explicitly annotate it as being in type I.O., because then the compiler will specialize it all. If you write lots and lots of very generic code and the compiler does not specialize it, then there would be a cost. But if you want to be careful, you could ensure that it always did specialize to the I.O. type. Because GHC is very good at specializing to particular instances of classes. Because all of those type classes, the I.O. instances, are exactly the thing that you would have written anyway. So it's a very straightforward specialization.
Yeah, thank you, Duncan. Thank you for the question.
Any other questions right now?
Yeah, don't be shy.
Okay.
Yeah, thank you, Andres. Okay. So where were we? So as you can see, there's evidence in the trace about the scheduling of threads. So we have the main thread here always appearing, and we have the thread that is going to run the timer. That's the -11. That only appears when the timer expires. So before time 1000, the first line that appears time 1000, and the previous one, you can see event schedule blocked. So that's the main thread blocked on waiting for the timer to expire. So you can see it's very granular in the way that you see all these I.O. events that are happening with timers. I have examples that we're going to see later about TVARs and STM transactions. It's all going to be very explicit. So you can already see that when the event timer expires, the time passes, right? And you can see that when the timer does expire, it triggers a wake up on the main thread. It sees that event tx wake up label tvar ID 0, and then the main thread resumes doing stuff. So you can see then that it's going to print, and the log appears in the trace, and then the main thread just finishes in under 1,000 seconds. So if you run this, you run a simulation that runs virtually 1,000 seconds in just a couple of seconds. So you can already see how one can use this power to do more fancy stuff. Okay, so let's go on. So testing. So we already saw the trace that one can get from simulating a program. Testing with this is just, I mean, you can obviously write it as you do with I/O. You run the program, see what the output was like. For example, if you have an addition function that for some reason runs in I/O, you can run the addition for multiple inputs, get the output, and check if it's correct, right? But more often than not, in distributed systems, you don't get output. Like the program that runs doesn't finish; it stays running for as long as it doesn't crash. So what we want to test in those sorts of programs are the traces. So if we have meaningful events that we want to analyze, we would log them. And then in the test, we will run the simulation, get the trace, get the meaningful events from the trace, and then write a property test about those meaningful events. So as I showed, these are some API functions that the IOSim API offers. You can run the simulation purely and get an output back. You can also have some strict shutdown that checks if all the threads that when your main program finishes, if all the threads were finished along with it or not. And you can also get the trace, obviously for testing purposes, that would be the one to go for more often. And there's also functions to get the meaningful events from the trace. So trace select trace events and trace select trace events dynamic are the functions that you want to use. There are also list variants if you don't want the trace data type that the IOSim offers. But yeah, so yeah, I put this slide here to remember me to talk a little bit about the quirks of IOSim. So it is deterministic. It's something that you would like in a simulation. And for testing purposes, you would also want to be able to reproduce the counterexample as faithful as possible. Another thing is that time only passes if you put a explicit thread delay, right? That makes sense because the way IOSim tries to simulate your code, it tries to run everything as concurrently as possible. So in the trace example that we saw a bunch of events all happening at time 0, and then a bunch of events all happening at time 1,000. Okay, so that is the weakest thing one simulation can assume about your concurrent program. You don't want it to assume that certain actions are going to take more than others. If possible, assume that everything, that we have infinite CPU power and everything runs as fast as possible. So this is important. Why? Because when we're testing stuff, right, we want to simulate time passing. So, for example, if we want to test how DNS works and DNS lookups, in IOSim, everything would take 0 time. So when we're trying to test things like this, one would have to write data type with an arbitrary instance that would randomly generate different delays for each action that you're trying to test. So yeah, that's something to have in mind. Another thing is the trace is as lazy as it can be. This is very useful because if you have a program that runs indefinitely and you want to test just the first 24 hours of the trace, you don't have to wait until the trace finishes computing and you get the whole trace. You can write your property tests in lazy style, and you can evaluate the stream as it is generated, and that has some performance and design benefits as well. Another thing that I decided to put that is that it's not a model checker. I was hoping people would ask me about this in particular, but it doesn't explore all the possible traces that one might get with a very complex concurrent system. It picks a scheduling, and it is deterministic in that way. It always is going to pick the same schedule for the same inputs. IOSim POR can give you a little bit of a taste of a checker, not a model one, but maybe a checker of different paths that one can take if it picks a different schedulings. But otherwise, it's not a model checker. The way we did this is that we wanted to have time passing, right? If we had a model checker, we couldn't analyze time passing, and that's useful more often than a model checker if you want to test stuff before going into production, because you can really make sure you ran for virtual time, like 24 hours virtual time or something like that. Whereas with a model checker, you will just be sure that all the paths were not leading to a deadlock or something like that, and it will be slower to execute as well. So this is like a good balance, I believe. Okay, so I'm not sure half an hour that this took. I'm not sure if you guys want to pause. Maybe you have any questions. I can go back into the slides and explain things more thoroughly.
I have two questions.
Sure.
One is, does this give you any idea about the memory footprint of your program, or just the execution?
Yeah, thank you. The IOSim library only deals with execution time and running things. So if your program or test suite, for example, is written in a style that would lead to space leaks, or it's just normal Haskell, right? And you would inspect it with a standard tooling that Haskell offers in that sense. But IOSim doesn't make any evaluations about memory footprints.
But if you run a 24-hour trace simulation, would it give you a hint if that would leak?
Yeah. So at IOHK, I found some problems related to that. So we were trying to run our Cardano node in simulation. And as you know, a blockchain grows with time, right? So I had this issue that I tried to run my simulation for virtually too long. And it took a lot of time because the chunks of the chain were growing and growing non-stop, as one would expect. So I had a memory footprint rather large. And it wasn't due to any space leak, but just the way the program itself allocates memory and uses it. So yeah, it would show you that memory is being allocated in that way.
Thank you.
Can I also answer that?
Yeah, please.
Yeah, I'll give it back to you. Yes.
And then Simon also.
So the question about like memory use, a very similar thing is, can you make certain resources visible within simulation? And the answer is you can if you make them explicit in your trace. So, your question about like, classic memory profiling would be the right answer for most things. But if there's certain things about like the resource use that are visible to your program, like the size of this map or the size of that queue or whatever, that you're particularly interested in, you can make that explicit in your program by tracing, at each stage the size of this queue, the size of this map. And then you see that in the trace, and then you can write graphs, plots, or properties that check that, the size of these queues never gets bigger than blah, blah, blah. So if you make it explicit, then it can be visible. But if it's just like the kind of pure parts of your computation or, keeping vast amounts of memory, then and you don't make it visible, then it doesn't help you. So we do use this for like simulations where we're trying to model the performance of systems. And there we have to, use the right thread delays to model like how long a computation is going to take, or, or certain resources being used. And then if you make those visible in the trace, you can get a lot of information out about your simulation. Yeah.
Andres, could you pass to Simon?
Yeah, he had another question.
Oh, yeah, you had
Is it
another question.
answered? Okay.
Sorry about that, I forgot you had another question.
Thanks. So you said that this is deterministic, right?
Yeah.
You can, so that's good because it means if
Very
you,
good.
you know, something happens, you can repeat it. But
Yeah.
what if your program is, well, read the price of Microsoft stock and then, you know, do something? Now, that's nothing to do with scheduling. That's come and get from the external world. So when you run it again, Microsoft stock might have gone down.
Mm-hmm.
So you must be not telling us something like you're recording the answers and keeping them back and be able to replay them or something.
Yeah, so as I said, IOSim doesn't run in I/O, so you couldn't do external API requests to get variable data.
Maybe that's the program I want to test. I mean, that's the program I want to test does I/O. That's why it's called IOSim, isn't it?
So the way you model that is you would write your test environment in a way that changes every time you try to query a different, the same API. So for example, you would have to mock the API into your test suite in order not to make the request in I/O, but simulate in a pure way to the request you get.
So when you said a drop-in replacement, you weren't quite being truthful.
Yeah, that's just to catch people's attention. But yeah, thanks for the question. Do you want to ask your question, Andres?
No, I don't, but I'm looking for others.
Is that the same for any type of input that you have to mock, like for example, stood-in reading? Or?
So anything that would be external I/O-like computations, you would have to simulate that as well. For example, when I mentioned the DNS lookups, those are things that happen in I/O, like you make a DNS lookup request. And the way I had to do that was to, like in simple terms, have like a list of a map from domain names to IPs, and that would change every time I would ask for a lookup. And then my test suite would deal with that implementation details just to make sure I was modeling DNS lookups faithfully enough. And that also has impact on the quality of the tests, right? If my DNS lookups were static, then I wasn't really testing anything interesting. So it's some sort of failure injection. That's another thing that you can do. You can make your lookups fail with a certain frequency, and you can look for more edge cases that way.
What happens if I use code from another library that runs in I/O? Can I plug it in there too, or do I have to write a mock-up of this as well?
Yeah, if IOSim or IO classes doesn't cover it, you would have to do it. So another example from real life is that we simulate sockets and TCP connections on our test environments. And that's kind of tricky to get, and IOSim also helps you detecting if the test is failing because it's something that would happen in real life, or is it just failing because we had a bug on our mock code somewhere. And most often than not, that was the case.
And I have another question. I still try to figure out what is exactly the place for this, the application for IOSim. So normally, I think I take some tracing framework and just put tracing statements in my code, and then run tests on the traces of the that are produced by the tracing framework. So I figured that this tries to achieve something similar, but just what was the reason why IOSim got invented? Maybe. Oh,
yeah. Duncan wants to answer that. Yeah.
So the original motivation was for testing concurrent distributed systems. So all this, networking stuff and this blockchain nonsense, it was about trying to test that. And testing, concurrent code is hard, and testing it is therefore even more important. So that was the primary original motivation, was testing networking code, which is why it has to include time, because like simulating network delays is absolutely crucial. But I think the additional, so I think now having seen it in production, there's really two very good use cases. One is exactly the original one of testing concurrent, distributed systems in a mock environment with quick check. Obviously, you write your mock environment, you can shrink it, etc. But the other one is for writing like discrete event things where you might otherwise use a discrete event simulator for where you're not interested in running it for real, but you are interested in it just for the simulation. So, for example, for modeling the performance of some system, if you want to model performance, usually this is meaning time or other things that are visible in a simulation, then yeah, so like doing models of distributed systems where you really care about what's the performance of that system going to be. So that I think is another very useful application.
Thank you.
Anyone else?
There. Yeah.
Oh, yes. Thank you.
Yeah. And not to mention that it's deterministic. So if you wanted to do that sort of logging in I/O and then analyzing the trace and making sure that the trace is consistent with what properties you want to verify, it's harder to if it's not deterministic. Yeah.
Hi. So actually my question was about the determinism and the model checking. Are those
scheduling?
No, the first one was determinism. Like you said, the limitations were determinism, and the second limitation was it doesn't do model checking.
Yeah.
Are those things that are envisioned for the future as like extensions, or is there a fundamental reason why you can't like include them right now? Because, for example, I think naturally you would want to play around with this and connect it to quick check or something, for example, right? And have the thread delays be stochastic, drawn from something, right? Is that something that you are planning to maybe incorporate in the future?
I'm not sure if that's in the plans.
Huh?
You can already do that.
You can already do that?
Yeah.
So you can have the thread delays be random?
The model checking.
Well, the delays, the control delays, you can already do. Because when you write your test environment, and the script for your test environment you generate for quick check, obviously, for quick check, you just generate how long those delays are going to be. And then quick check will generate lots of different things.
Oh, so you generate it as like an environment kind of input to the run of the model, right? And then it will look up what the delay should be. Okay.
Yeah.
So you can already basically do that.
And then what you mentioned about the partial order reduction variant, that is about exploring schedule variation.
Yeah.
So, well, in that sense, you don't have determinism as a limitation then, because you can inject non-determinism. Yeah, okay. But you on your slide, you kind of presented it as a limitation, but it's kind of like you can have it be entirely deterministic, or you can inject non-determinism as you need it, essentially, right? And I'm assuming you can probably do the same thing with model checking, because in the same way you can generate all of the different like environment inputs or whatever, like parameters essentially for all these different runs, and maybe do something exhaustive or something like search, right?
Yeah. The thing with model checking is it fits other use case. It's not a simulator, right? You would test different things. You would write properties in a different way. And the way the IOSim was designed was with the use case that Duncan said, to run things, have time passing, change different delays, and see what sort of components take more time or can be a bottleneck in that way. Obviously, with a lot of effort, you can probably get that from model checker. The problem is model checking concurrent systems is really, really unfeasible in sometimes. And when you have code base that is very large, and if you want to do exhaustive model checking on it, it's sort of very difficult to get results in real time and get a constant feedback loop while you're developing. But yeah, I see your point, and it will definitely be something of value. But right now, I think IOSim has a nice trade-off on what it can achieve and its limitations for our particular purpose. Thank you for the question.
Anyone else?
One there. Andres?
Sorry, so the room is
Thank
just
you, Andres,
too
for making the round trips. It should have been me, I think.
So let's assume that I have a huge I/O application.
Yeah.
How am I supposed to use IOSim basically to check concurrency and things? Like, am I supposed to rewrite it or?
Yeah, so if you have a very large I/O application, the best thing to do would probably separate into the components you really want to test, because it's really large, right? And then it depends on the sort of features that your I/O application uses. So if it does a lot of API requests or gets data from external sources and whatnot, you would have to model those if you wanted to get a simulation out of it, right? You would have to simulate all the I/O parts that are not covered by IOSim, in that sense. If you wanted to test it, that is. If you wanted to run it and test it, yeah.
But can I have the same code base both for running and for testing? So I need to...
Yeah. Assuming you use only the subset of I/O that I/O classes and IOSim supports, which is really extensive. Like if you use STM, async library, timeout calls, and that sort of stuff, then you can, with very low effort, just replace your type signatures to use like constraint-based notations and parameterize your monad over any arbitrary monad and then instantiate it to IOSim, and it should work.
Thanks.
Like I show with this example here, it's very simple, but I have one program specialized to I/O. I only have to change the put string line call to say, but if by any chance I had like with a sync there or a fork I/O there, then I wouldn't have to change anything, only the type signature to make it polymorphic. Yeah.
So any abstraction usually comes at a cost of performance, and especially here whenever we parameterize on a monad. And as far as I know, GHC will not be as great as optimized if it was just restricted to I/O. So how does switching to IOSim model affects the performance of the actual program?
I think we kind of answered some questions from that.
But on a concrete example, like benchmarks.
We don't have specific benchmarks, but you can expect to have a large overhead. If you run I/O and then you want the same results in IOSim, there's an overhead of running the simulation. Whereas, as Duncan said, if you specialize your type in the type signature to be I/O, the code should just specialize by itself.
At worst, if you wrote your function which was parameterized over all these classes, and then did a specialize it to I/O. So this question came up slightly earlier, and I think the answer is you can get the zero overhead with if you use specialized pragmas, to be really careful. Yeah, so you'd have your generic, like go on to the next slide, the sort of generic versions, and then if you also had a specialized pragma that said, and specialize this one to I/O, then GHC will pretty much guarantee to get rid of all the overhead, because the overhead is, it's just looking up the type class things, and they're just direct one for one, so there should otherwise be no overhead. Without it, then it'll depend on how well GHC will specialize, which, if you're using it directly within the same module at an I/O type, again, it'll be perfect. In a cross-module case, it'll be like, well, depends how big the function is. Does it want to inline it or not? Yeah.
Yeah.
But if there's a specialized pragma, you can be pretty confident, I think.
Yeah.
I have a small question, because you mentioned, like, if the code happens to be within those classes that are already supported. So what if it's not? Is it easy? Is it easy enough to add new features to IOSim?
Yeah.
Or is that something
I have
that
a
you shouldn't
slide about that here. So it goes over This is the demo. So this is the source code structure, more like. So it's all written in Haskell, what, 2010 standard. And if you just wanted to add a new effect capability, you'd go over to the IO classes. I don't think I have the structure for IO class here. But IO classes is where all the type classes are defined. So if you wanted some fancy feature that IOSim does not support, you can add your own there, write the IO and IOSim type class instance definitions for that particular type class, and then probably make a PR or something.
Okay, but I need to patch the library. I cannot do it. I cannot do it in a sort of a
I think you can kind of do. Yeah, Duncan is eager to answer that.
So if obviously you can do it by patching the simulator itself. But let me give an example. So again, this is blockchain nonsense. We wanted to test the disk data structure components of this blockchain node. And so obviously, interacting with the disk, you have to have all these file system effects. And the IOSim does not support like file system effects. So what's the answer? The answer is abstract. So you have an interface for all of your file system interactions, open file, blah, 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 read, write, all that kind of stuff. Just a big record of all those methods. Then you have I/O implementations of those. That's the ones that actually go and do things on disk. And then you write an implementation of that same interface in the simulation, which of course then mocks a file system within the simulator using existing features that do exist within the simulator, TVARs and whatever. And at that point, you can then start to do things like fault injection. You generate scripts of, the third I/O operation will fail with this result, whatever. And so we are able to test, our on-disk data structures in the context of a fully running node, and giving all this, fault injection, so we can know that it, correctly recovers from file system exceptions or silent data corruption. So the answer is yes, you can extend it, but you extend it by mocking it basically, and doing that within the simulation. Within a simulation environment, where you have then complete control over what those effects are going to be and failures, which it's something that's really hard to do if you can't get underneath. It's very hard to get properly test file system failures unless you can get between the program and the file system to be able to do that fault injection. So that's one way to do it, and it's very effective. It requires a bit of overhead setup to get going. But once you've got it working and you've got your quick check shrinking working, it's absolutely wonderful for finding bugs and then diagnosing them.
Thank you, Duncan. I hope that answered your question. Yeah, one more here. Yeah. Thanks for all the questions, by the way. Otherwise, the talk would. No. We have time. We have as much time as it needs, though. Yeah.
Yeah, so you just mentioned that you can mock, for example, file system using pre-existing features like STM, but then wouldn't those intermediary STM operations show up in the traces? Is there a way to hide them, or?
That's a good question. Yeah.
You're generally not interested in the low-level details of the trace.
Yeah, so the trace that we just saw, most often than not, you don't care about all that stuff, right? You just look at it if something really weird happens with STM, or the way the value that your TVARs have may not be what you'd be expecting, and let's look at the most detailed thing that we can have. But with testing, you just get the meaningful events you want from the trace. Like I showed you, you can use these functions. There are more in the API. They take the trace and give you a trace of a particular type, and that particular type can be this trace example type, for example, right? So you can use trace select, trace events dynamic, put type annotation that you wanted your B to be the trace example data type. You get all the events that have that type, and then you just write your properties over a trace with meaningful events. obviously, if you wanted to, and I think we do that in the IOSim test code to test that if the STM actions are semantically correct to what one would expect in IO, I think we do inspect those logs that are very detailed.
Yeah, that answers. Thanks.
Yeah, nice. Okay. Yeah. Cool. One there, one more there. Yeah, no, keep them coming. We have a demo afterwards to show more contrived examples of how we can use IOSim and check the trace. So that might spur more questions as well.
So you mentioned that you intend to also use this maybe on larger programs, right? Like with a lot more complexity in them. And I think testing, as the program becomes larger, becomes more, becomes more of a data science problem, right? Because you're doing a lot more runs and you're like really searching for like the problems and stuff. And I saw that, okay, so you have this data structure, the trace, the SIM trace essentially, and you can filter over it, right? But do you have any plans to have some way to write this into kind of analytical databases or something optimized for, and more optimized for analytics than simply scanning through and applying a predicate? You know,
yeah,
you know what I mean?
Thanks for asking that. I can touch a couple of points about that. So if your simulation is really detailed, right, which can happen when you simulate networking, low-level networking, like passing messages, TCP packets and whatnot, which are really fast, like 4 microseconds or milliseconds, and there are a lot of them. So for example, if you're testing if your network protocol is correct, you'll see a lot of message passing. If you model your program in such a granular way, your simulation trace is going to get huge and your simulation execution time is going to be very big. And it can generate a lot of bytes of memory and take a lot of time to actually analyze the whole trace. So that can be an option. I mean, you can always like manipulate the trace into the format you want to upload it into. But I'm not sure if there are plans to make something built into IOSim.
Well, there's 2 dimensions here, right? One is how complex like one run of the simulation is, like how long is the program, and the other one is the parameter space essentially that you are kind of simulating over, like you're choosing different parameter sets that you run the same program on, and maybe you want to do both, like explore both in a sense, and then analyze them to see kind of, you know, where failures occur. Maybe there's a theme.
I'm not sure I'm understanding the question. You're mentioning parameters.
So one is like the complexity of your program, right?
Okay.
And the more complex your program is, the longer your trace is going to be, and then you know you're going to want to filter over that.
Okay.
But the other one is the initial inputs, like the parameters that you run, like that you put into the program before you run it, right? And you can use different parameters to have different runs, and then you want to maybe compare across them and stuff. At a certain scale of like the parameter space or of the program complexity, I think just having a simple in-memory, you know, SIM trace data structure might become less efficient to be able to do that.
Yeah,
right?
Absolutely.
So
yeah, you're absolutely right.
A better
so
analytics framework.
if you have a ginormous program with ginormous input variables, a deterministic and discrete simulation framework might not be enough for what you're trying to do. It certainly, at least I have fallen into some form of that bottleneck. But it all has to do with the way you structure your like testing environment. So for example, that could be a sign that you're trying to do a lot of stuff at the same time. It might be easier for you to focus on just one property that only is related to a certain set of inputs and a certain part of code complexity. That can maybe divide your problem down into feasible parts. But yeah, if that's not possible, then you're absolutely right, and you'll get a very long and hard time simulating this and analyzing it.
Thanks.
Yeah. Thank you. Cool.
Okay.
Yeah. So
I think we should perhaps.
Yeah, let's continue. If you have any questions, feel free to raise your hand. And Andres, thank you once again for helping me with that.
That's what I'm here for.
Yeah. So I had a demo prepared. Let's see if I can make this work. If I can just put the code here, then put this in full screen. And it's too small. Can everybody see the code? Is it too big, too small? I think it's all right. Okay, so this is a very simple example. I'm not actually going to run it, but here on the right side is how you would write a very simple main program that outputs the trace of your IOSim programs. So on the left side, you have all these imports. As you can see, I have control monad, IOSim, control monad, class monad say, and all the type classes that my programs should be using. And then you have, so it works with normal control.monad functions, since it's also a monad, IOSim. And very simple program, only requires the say capabilities, so we parameterize it over M with a constraint monad say. If we want thread delay, one has monad delay, as we saw previously. This is the example on the slides. But then, if we want to have a not so simple example with concurrency, this is what it would look like. So let me maybe make this like this. Okay. Then on the right side, you import the IOSim code. This is the demo module that is in here. And then you have a trace, which is a string. I'm using prettyprint trace function from the API and runs in trace that I showed you on the previous slide as well. And the.example is exactly the first example we saw there. So this is, in a nutshell, how you would write a program and use it to run and get the trace out of it. So let's just, for science, look into model example 5 here, which should work just by changing this, saving, and let's first go through what it should do. So it should create a new TM var, new empty one, and 2 threads. Each thread is going to take 5 seconds before putting a value inside the TM var. Okay, so this ought to be a race condition. And one of the threads ought to be blocked because the first one that puts it in is going to block the other one that tries to put as well. Then the main thread is going to take the TM var out and print the output and exit the program. So if I come here and close everything and maybe do cabal run, this is going to build the program. So you can reproduce everything that you're seeing here by yourselves. The repository is pretty much self-sufficient at this point. But yeah, you can see here there is a lot of detail in these events. Most of them you don't care, like scheduling of threads or transactions that are committed. Maybe you do, maybe not, but you can see what's happening here. So it's creating the TM var here. So it's committing a new tvar with an ID of 0. And then it's forking the 2 threads. Notice that everything is happening at time 0. Because these are all actions that can possibly happen at the same time. But the order of the events that you're seeing here is the actual scheduling of those actions that was picked. Okay, so for example, if you wanted the event timer created at a different point, you would have to either put a thread delay here or have your test environment, generating different thread delays in order to get a different interleaving of events. So yeah, creating a TM var, forking the threads, logging, waiting. So not sure where how to put the code hand in hand, but we'll go back into it quickly. Logging, creating the timer. This is a thread delay for the first fork thread. The first fork thread is going to run all the way, so you can see here that the timer created, timer expires here, and we see all the transactions that are blocked here, and when a transaction is committed, things wake up here. So I can see where oh, okay, yeah. So the first thread puts the TM var, the integer into the TM var. The second thread blocks on that TM var. The timers expire, and then you can see that the thread with ID 1 computes the result and logs that. And then the main thread wakes up since the TM var was committed. And now the main thread, which was blocked on waiting for something to take, is able to do that. And then the answer is 42, which I believe is the first thread that wins the race. Let's see. Not this one. This one. Yeah, so the first one is 42, the second one is 24, and the value that we see on the screen here is 42. So really quick, if one would ask for a different interleave of threads, maybe put this into 6 seconds and run, recompile, and now we see 24. Because now the timer that expires is the second thread one, and you can see that it doesn't even reach 6 seconds because the main thread unblocks and you don't see anything else. So if I had run this with run seems strict, I think that's how it's called, this would give me an error because there are still threads that didn't finish nicely. Okay, I think you get the point here. So this is also to highlight and illustrate how you can pretty much run functions that you would in real I/O, that they're not that much of a different from IOSim. For example, this one. So yeah, not sure if you have any questions. This is just to highlight and show more complex examples. Yeah? I could. Thank you, Andres.
Can you go back to the example 5?
Above?
Example 5.
Example 5.
Is it easy to simulate asynchronous exceptions whenever you do testing in order to figure out that one thread was deadlocked?
Yeah, I also actually have an example for that. I forgot. I think is this one. Yeah, synchronous exception is an example. So,
but what I mean is during testing, whenever you do inject asynchronous exceptions at a random point inside of the program, right?
Yeah, that's very useful. IOSim is very useful for that. So if you have a lot of concurrent code that can receive a synchronous exception and you forgot to mask in the correct place, you can find these sort of problems. I'll show you with this example. So we have a loop here that is doing an important task that you don't want it to be interrupted, right? You don't want it to leave it halfway. And it's doing it in a loop. And then you have 2 threads. One is running the loop, and the other one waits 5 seconds and throws an exception, canceling the thread, right? So it might be the case that while this loop is doing the important task, it gets shut down. So you can see that there's a bug here where this important text should be masked for asynchronous exceptions. So it doesn't receive an exception and leaves halfway. It should receive the exception, hold on and do some cleanup probably, and then cleanly exit and close the program. So yeah, let's run example 7. And we can see IOSim telling us that an asynchronous exception has been received. Maybe, yeah. So there are a lot of, oh, no, not really a lot of events because I carefully put this into. Okay, so let's see. One thing I'll do is to label this thread, so we can see it clearly on the trace, and rerun the simulation. Okay, so now here we see the main thread and the loop thread. So here the loop starts the important task, it finishes, it goes back around and round, and then after 5 seconds, which is the time where the main thread throws the asynchronous exception, we should see an event throw async canceled, right? So the main thread then starts throwing the asynchronous exceptions to thread 1, and thread 1, which was doing the important task, finishes. And then the main thread finishes everything. So if you have a test that checks that each pair of starting important tasks that appears in the trace should end with an accompanying finished task, and the test fails with an failing to finish important task, you would know that some asynchronous exceptions are going on here, and you would put the mask in the right place. I think that's, hope this highlights your problem. Cool. Yeah, so it should print starting important task and finish important task in pairs. In that case, it didn't happen. Okay. So what time is it? So 2:42. I think we have about 1 hour. Let me just go over. If you want to contribute, this is the sort of structure. It's really simple. We have a module for common types to be shared between IOSim and IOSim POR. But the things that you should be looking at is the types.hs, which has the internal DSL for the simulator actions, such as timer, exception, forking, etc. There's a different type for STMA. I can go into more details about the implementation if you have the questions, but I just sort of thought this was a good idea just to skim over this. And then IO classes has all the instance implementations for IO and IOSim. Okay. So if you're up to it, I have a small project that you ought to try. Writing it in IOSim and testing it and see if everything, if your implementation is correct. You can put the pieces together, write the program, and then write a small test suite to test everything. Otherwise, I can just try and do some live coding, which isn't as fun. But the prompt is the classic readers-writers problem. Basically, you have a shared memory where threads can write to and threads can read to. You have to be careful about race conditions, and that no writer is writing while a reader is reading, and vice versa. So I put some useful properties that we ought to test. So no reader should be able to read while someone is writing. No two writers should be able to write at the same time. And one obvious one is if the last writer writes an X, something to the shared memory, then the first reader to read it should also read the X. So not sure if you're up to some coding now, but maybe someone could tell very briefly how we go about and try to write a property test for the first property, or even write a program from a very high-level perspective. What do you say? This is more like a interactive part of the workshop.
I think we should
do it. Do it? Yeah? In groups? Okay. Yeah, you can find the repository here. It has all the. Let me get this. Here. Yeah. I think I scared some people. But yeah, if that's a bit of a burden, then I'll just go over myself and I'll try to highlight what can be done. So you'll do it with me then. Here. Okay. So the people that are staying do want to try it for themselves, or should I kind of guide the implementation and you see how it can look like if you do it yourself? Do it yourselves or myself? Myself? Okay, yeah, that sounds good. So we'll split the time, half an hour, you try to figure out how the library works and write some code, and then I'll show my proposed solution. Yeah. Yeah, I can go around and, yeah, it's already in GitHub. You can take a peek there if you're kind of stuck, but I can try and go over each group and answer any clarification questions or whatnot. Yeah? Yeah, go ahead.
Why exactly didn't you use existing effect framework and just write the type that can do all this and write all the effects?
That's a good question. I'm familiar with some type effect systems, but for this particular one, we wanted to simulate. So it's kind of for a particular use case. So if you want to write an effect for an effect system, like a simulating one, you probably want it to be more general and abstract and probably more like a model checker maybe, possibly. But you can definitely use this one as an interpretation. Yeah, you can if you have a code base that use effect system. Is that you're going at? Okay, no, but that sounds about right. So if you use any effect system and you want to instantiate either to I/O or some simulation thing, you can definitely use IOSim for that. I mean, it's a monad. You can substitute it whenever you like, or maybe I misunderstood the question.
So I think we should say 10 minutes to give everybody the chance to actually look at the repository and get started.
Okay.
And to actually do something, and then you'll just start walking through it as well. And if people want to continue on their own, they can.
Okay.
But otherwise, I think if people don't want to do it on their own, like half an hour is too much, right? So
okay, yeah.
So I think
that's
I think that should be a compromise. And in between, if you have any questions about how to get started, Duncan or Armando can answer them, right? I probably can't. But yeah.
Yeah.
Now, can you just switch to slide?
Yeah, sorry about that. So the repository is here. It's under the well-type organization, and then IOSim ZuriHac 2022. Okay. Hi, everybody. Thanks for staying in, and probably you gave it a try, looking into the repository. So in the screen, you can see like some sort of direction for implementing this prompt. So the way I implemented this, and you can see it in the repository, I have a lock mechanism that has a state. And the state here can be free, reading, or writing. If a writer thread is going to acquires the lock, then it sets the lock state to writing. And if a reader thread tries to read from it and finds it in state writing, it should wait just for the state to change, right? So let me put here. I'm not sure. Do you want to maybe make a comment on how you do it or how you were thinking of doing it? Otherwise, yeah, please do. I think that's her over there. Did you raise your hand? Okay.
What I wanted to ask was, how can one then mock this I/O for exception for errors to be simulated, just like you have explained?
So you do it just like you do in I/O, as you're familiar with?
Yeah. But to say sometimes that you sometimes that works fine, but every third time.
Okay. So that would be, so here you'll just focus on the implementation, right? And you would assume you're writing against I/O, for example, if that's easy for you to work with. Then if you want to test this and test those properties there, right? And you want to inject failures in them. So you would have to write, let me just pull up my proposed solution here. I think it's...
What do you mean generally?
In general, yeah.
Yeah, so for the test suite, you have like a test environment, where in my case, I have like the number of reader threads, the number of writer threads, and the things to write to the TVAR. And then I have an arbitrary instance that basically generates random number of threads just to spin up a couple of threads. What happens if I run one reader and no writers, 3 readers and 2 writers, that sort of stuff. Yeah. But if you wanted to inject failures, you could add a thing here that would be a list of diff times, and then you would basically make the threads fail after this value. Am I making sense?
Yeah, this makes sense.
So for example, then in the code, I would have to make my functions here. Where is it? Oh, here. Nope. I guess I'm doing, not sure what I'm doing here. Let me go back and fix this. Yeah. Okay. So in my code, I will have to maybe feed here a value and then put here, sorry about that. So this is my, it's a bit hard to, so run read write, right? And then whenever I get my diff time here, right? So this is the failures list, right? And then I would get the head here, I'm not going to write the whole code, but then when I spin the writer threads and the read threads, I would pass the value here. So fail at would be a value of this list. And then when I write in my writer thread, which I'm not sure where I have defined it. Nope. Nope. Yeah. It's a bit hard to see from here. But if when this function is defined, I could add a new parameter that would time out after a certain delay and kill the thread. And that wouldn't happen in my business code over here, which just deals with acquiring and freeing the logs. Here, this code would basically test launching a bunch of reader and writer threads with a certain delay to fail and be killed. Here, I wish I could mirror my display so it would be easier for. Yeah? You don't have this on your screen? No. Yeah.
But then interactive coding is going to be very difficult.
Yeah. I think it's over here, actually. Yeah, it's here. So I just put a parameter here and fail at and do like a timeout, sort of. And then when I was going to test this code, then this thread would be killed at a particular time, and I could inject failures like that. This was a bit rough explanations, but I hope you get the point here. Yeah. Okay. Any other?
Yeah, and there is another question on top of this. Have you tried also to do this kind of interactively in terms that you decide that you change this ratio of failures and stuff like that during the tracing execution of the simulation?
Changing what exactly?
For example, you run simulation, right? And then during the simulation, you try to tweak the failure ratio or stuff like that.
Yeah. So your generator could take that into account. So when writing the arbitrary instance for your test environment, the failures, the list of failure diff times that I showed you, every time I would run a new test, that list would be different. And then I could try different thread delays for executing the reads and writes, and different thread delays for failing the threads at different times. So I could explore more and have more coverage and make sure that I was testing writers dying while readers were reading and vice versa, and testing if I was cleanly freeing the logs in case of asynchronous exceptions, stuff like that. That was I don't have that in my proposed solution, but you could definitely inject failures in your test suite and check for those failures as well. Yeah, Thank you. Andres? Yeah, so as I was saying, this is the mock structure for my proposed solution. Have some log state, free writing or reading. The log is going to be a tvar with a certain value, and this should be the log state. And then my meaningful events would be whatever I think I want to inspect. So, for example, if I change to my slides here, if I want to test that no reader should be able to read while someone is writing, right? I should have information when some thread is reading, when some thread is writing, some information about when some reader stopped reading, and the same for the writer thread. So in my proposed solution, I do have these RW events: start reading, read, stop reading, start writing, wrote, stop writing. And when I start reading, after I acquire the lock, I trace that I'm starting to read and that I'm effectively reading. The same for writing, and the same for stopping and wrote. So then when I inspect the trace, and I want to check that no writers while someone is reading, I run the simulation. I select only the event, the trace events that I care about, which are these ones. And then I write my property against the list of meaningful events. And I hope I did get this right, but basically the property is I have the state of my lock during the execution. It starts as free. When I start reading, I put my state as reading. And if I, by some chance, find that someone started writing while my state was reading, then this should not happen. So similarly to the example of the important task that I showed in the demo, start readings and stop reading should go in pairs, and start writing and stop writing should go in pairs as well. Nothing in between. And obviously you can expand this with multiple readers at the same time, because reading does not mutate state, and my solution does account for that, but that's the gist of this property. You can see it's really simple, something like that. This is a property for no writer should be able to acquire the lock and write while other writer thread is writing. So it's in the same style, but I swap the reading with writing here. And here is that reads are consistent in the sense that if some writer writes A, the next reader that acquires a lock should read A as well, as long as no writer wrote before. And it's all in the same style. You just go over the trace and you check for the property you want to test. So this is in a nutshell. I'm not sure if your reasoning was going to lead to something like this, but I hope I've illustrated how simple and efficient it can be working with IOSim. So any feedback on that? Yeah? It's already in the repository. Yeah, it's called Project Soul. It has this name. It's under source, this code, and this code is under the test folder. Yeah. So arguably my solution can be wrong, but I wrote some tests to defend myself. Yeah. I was kind of hoping people would chime in with their solution and we'll run the property test and see if it failed or not. But I did find one in this particular test because I misspecified my property. I forgot to... If I found a stop writing and someone had started writing previously, I had to reset the state to free. And I forgot to do that, so I was getting counterexamples.
That's good, but also, I mean, John Hughes is always saying, like, right, if you have a program and you write your property tests and they all just succeed all the time,
yeah.
Right, then you should introduce bugs in your program deliberately and see whether any of your tests fail.
Yeah, that's...
is that something...
That's something that I could do. I'm not sure if I have the time, and my neck is not that elastic, but if I wanted to do that, so I did have to add this to write data here to test that, where was it?
So I'm paraphrasing something, and I don't want to put words into his mouth, but essentially you should not trust a test that has never failed.
That's
right?
entirely correct. Yeah. So if I wanted to inject failure somehow, I'll try to do it more cleanly than I did it before.
Yes.
Ah,
Yes.
okay, I see. So let's.
Yeah. Yeah.
Ah, okay.
Because it's very easy to make mistakes in your properties, right? And
yeah.
And
let's just switch this.
If you cannot make them fail, then something.
Yeah. So I switched something that should go very wrong, and I have to go back here. So cabal test. Oops. Ah, yeah. Probably. Let's see. Okay, three tests failed, obviously. So the no write while read test failed after 11 tests and 2 shrinks. With the exception thrown while showing test case, stop writing lock in freeze state. So basically, when I called the stop writing function, it found a freeze state instead of a writing state. So it found an inconsistency here, which probably means my tests are robust. The same thing for all the other ones. Thanks for the suggestion, Andres. One question there?
Yep, thank you. So if you have now this test failing, how would you go about
fixing
debugging it? Yeah.
Yeah, so that's a good question. Thank you. So I could go over to my code, and if I didn't understand what's happening, right, I can analyze the trace to see what's actually happening inside the code. So it's just a means of printing the, where is it? So yeah, counterexample. I think I've missed one, or was it showing here? Oh, right. Okay. Yeah. Let's fix that real quick. Yeah. So here probably I'll do nothing. Okay, let's see if the test still fails. Yeah, it fails. And now we can see the trace. Yeah, I put a counterexample there. So failure deadlock. It's even uglier than I was hoping for. So basically you can see here a more detailed trace for this test, which I print the whole trace. In the latter ones, I only print the meaningful event. So you can see that I have a start writing, a stop writing, a road, and then I deadlock in this particular thread, in this particular writer thread. So I have a writer thread that deadlocks for some reason. And if I look here, this test is the no write while read. It also finds a deadlock, and probably I can inspect this to see what's happening. But I wasn't prepared to find such a example.
This is why shrinking is so important.
Yeah, the example is too big. I do have, but yeah, that was one, I think, this one. But I only have the meaningful events. So I was hoping to see some action on TVARs and TVARs threads getting blocked on something. But, well, I hope this illustrates how you could debug this. I mean, on the spot is a bit hard for me. But yeah, you could analyze this. You could see where threads get unblocked, which TVARs get committed and when. You can see that this potentially can all happen at the same time, but this is the scheduling that was picked. Probably if you have failure injections, you'll find different interleaves and probably find deadlocks in a different way. But yeah, I hope that I could power through this whole trace and give you the answer, but yeah. It's just too big, and I was not expecting to see it. But yeah, you could definitely do that.
Yeah, it's really worth writing your shrink groups for your test environment, because it's really important to get those short traces of see where the bug occurred with a minimal amount of stuff. And then it's not really quite straightforward. Whereas if you don't have shrink groups and you get like really blocked, then you're screwed.
Yeah, so probably deadlocks because I don't free anything, and then I have a bunch of threads waiting for acquiring the lock, and those threads never acquire it, so it's sort of a deadlock in that sense.
Yeah, but it's only a shrinker on the test environment that you've written. Because you're generating that testing environment. And so, you're generating that thing in the first place. And for shrinking that, there's some tricks you have to do for shrinking. Usually it's not.
Yeah.
And it's worth it. The effort is worth it.
So for example, if I forgot to, if I instead of freeing, I would put like reading, I'll get some sort of failure. No, forgot something. Why is this? Oh, yeah, because I have to put reading and then number. Yeah, so the test fails with a deadlock as well because I forget to free the state after reading, and it just deadlocks. And if I look at here, probably I will see a log that stops writing but does not commit TVAR with the right state, and then I will see the other threads not waking up correctly. Not sure where in the trace, but that's what probably is going to appear somewhere here somehow. Yeah, I can see thread 2 blocked on the TVAR, and then it just ends, and they keep being blocked by the TVAR. Oh, yeah. Okay, where was I? Here. Yeah, so not sure if you have any other questions. Yeah, so IOSim can detect deadlocks. It just looks if you're waiting on a TVAR and then the main thread finishes or something like that, or the main thread is blocked. If the main thread is blocked, then there's no chance that there aren't any other threads scheduled to run. That means you're deadlocked somehow.
If none is detected, all threads in the entire simulation are deadlocked. Then it detects deadlock. It can't do fine-grained deadlock. It's just if there are no threads you can run, but none of them have exited, then you're deadlocked.
Yeah. And it can detect live locks as well because your simulation won't finish. And it just keep generating the trace as well. So, yeah. Well, I think it's a nice place to stop if you don't have any more questions. Thank you.
I have a meta question, which perhaps is good for the end, because I'm not sure whether you have a good answer for this, but I think this is all very cool, personally, but I feel like when I start a new project, I'm probably going to start using I/O under normal circumstances. I'm not going to start a project by saying this is so critical that I need IOSim. Yeah. And then if the project has grown to the point where I feel like I had better used IOSim, it's probably a huge effort to actually rewrite it to make use of it, even though it is a sort of almost drop-in replacement, but you need to check all your dependencies, you need to abstract new interfaces, you need to do this and that. Is there like any additional advice you can give except like, yeah, you have to just do it from the beginning, you have to foresee all the problems and do it the right way from the start, or is there?
Yeah, so my advice would be the same I gave for that man that is no longer here, where he asks if you have a very big and complex program and a large input parameters that can probably slow you down if you want to pass everything into IOSim, I mean. It's just to focus on the properties you want to test, see how many components that property interacts with, and start building from the bottom. And that's kind of
you mean go to some kind of hybrid approach where you're only like using IOSim?
If you have a whole monolith program application, then sure, you're going to have a lot of trouble porting it into IOSim. But if you have small components and your property interacts with 2 or 3 of them, then you can start small, and that's actually how we did it at IOHK.
Okay.
We tested each component individually, and then we tested all components working together. And obviously, that takes a lot more effort to do, but after having done the smaller ones, it was incrementally easier. Thank you, Andres. Yeah. So,
any other final questions? Duncan wants to have the last word.
If people want, I can show a 5-minute demo of something using IOSim that's completely different with dust blinking lights.
Yeah. I think people
with graphics and animations.
Yeah, please come here.
This is strictly bonus material, so don't feel you have to stay for it. So this is an alternative use case for IOSim. So instead of, all this stuff we've been looking at so far has been all about, property testing concurrent code, which, you should do because concurrent code is really hard, et cetera, et cetera. But you can also use this sort of stuff where you might otherwise be just writing a simulation. Perhaps you can help me with the audiovisual stuff. So if you would be doing simulation as part of prototyping, for example, right? So in my case, I'm looking at I'm doing some prototyping of a distributed system, and I want to do some modeling. I need to mirror this. Hold on. Otherwise, I will go mad. Mirror. Apply. Yeah, okay. All right. So the context here is that I want to do some modeling of a distributed system. This is going to involve TCP. So I said, okay, I need to have a reasonable model of the performance behavior of TCP, because it's going to turn out to be crucial for my distributed system, because I'm actually really interested in modeling the performance of my distributed system. So I said, okay, let's start with a model of TCP itself as a smaller component of a much bigger simulation. So what I want to show here is it really fits. Let's make it this bit bigger. Big enough? Yeah. Right. So this is in exactly the style that we've been seeing today. So we've got all of the monad blah classes. So this works in both IO and IOSim. But in this case, I'm not ever going to run this in IO. I'm really only running this in IOSim because I'll be using that as my environment for writing. I'm just using this as a discrete event simulator, but able to write stuff using the full power of STM, threads, all the rest of it. So this function is going to, given some specification of the properties of this TCP connection, its latency, its bandwidth, etc., I'm going to construct 2 channels, or two channel endpoints, and then I can read and write each end of those channels, and then I can write simulations that connect a bunch of nodes together with TCP connections. And just as we've also seen, the tracer, we're using the same tracer stuff. Oops, sorry. keep jumping around. Exactly the same as we've seen already, just using the contra tracer stuff. In this case, what am I tracing? I'm tracing interesting events about the TCP execution. Now, so I can use that to build bigger simulations that use these TCP channels, but I can also then run that in simulation and plot or visualize the output of the simulation. So in this case, so maybe it's a bit small. What we're looking at is this is a GNU plot output, but it's produced from getting a data series by running the simulation. In this case, it's simulating a single TCP link and sending a bunch of messages in one direction. And this is showing us the classic slow start behavior of TCP, that at the beginning TCP is really slow because of the way it works with lots of messages going back and forth before it starts going a bit faster in the end. So this is on the x-axis we've got time, and the y-axis we've got the cumulative amount of data sent. And so as it happens, for like a 300 millisecond latency, so that's like here to Australia, it takes like 5 seconds to send like a megabyte of data or something because of this slow ramp up. Then with exactly the same underlying simulation, we can also, taking that same trace of execution, interpret that trace in an additional way, and we can build animations. So in this case, this is animating the exact same data. Let me make this a bit bigger, and I can zoom in a little bit. I think if I do that, whoop, there we go. So this is visualizing the behavior of TCP with all of the bits and bobs going back and forth. It's like there's a bunch of messages on the left-hand side which are queued up, waiting to send, and then the messages arriving on the right-hand side. And what this shows you in an animation style is getting across that idea that at the beginning it's really slow, and then it gets faster and faster as it is able to send data continuously rather than having to keep waiting for ACKs to arrive. So in this phase, it's now like going really quickly. And then you can do exactly the same thing, but now build up like larger networks of stuff. This one is this is now actually starts to be useful to show other people, because we can start doing comparisons of like 2 different networks with slightly different properties, and then you can visualize what the difference between them is. So in this case, if I remember what it is correctly, so there's 3 links, 4 nodes. We're sending the same amount of data in both cases, but in the top one, we're sending twice as many messages, but they're half the size and with double the frequency. So like whereas the bottom one, it's half the frequency, but the messages are twice as large. And this was meant to illustrate a point about TCP's congestion window collapsing back to the initial size if you wait more than one round trip or something. So the traffic pattern on the top gets you much higher throughput than the traffic pattern on the bottom, even though the latency and the bandwidth of all those links are exactly the same in both cases. So anyway, it starts to become useful to see performance behavior, although it's completely in a simulated environment. Yeah, but that's actually not very hard. Here's like you can't see the line numbers that easily. This is like 250 lines of code for the pure part of simulating a message send. It's really just keeping track of, how long does it take for things to get from here to there? How big are the segments? It's not that much code. And then once you've got that pure projection of what it's going to do, then turning that into the concurrent version is quite straightforward. So here, what we're doing, we're setting up a bunch of the sending and receiving buffers, and it's bidirectional, so you have to have 2 of them. And then the transport part, where is it here, is relatively small based on top of that pure model of TCP's behavior. So this is just, this is all the IOSim stuff, getting time. We're doing STM transactions for reading from the buffers and writing. and then we'd have just a priority queue of like when the acknowledgements are going to arrive. It's not that complicated. But it produces, very nice results, which then you can show to other people and help them to help them to understand why TCP is so weird. I've not published it anywhere, but I could do. It's not like proprietary. That's just what TCP is like. And by the way, Quick and all the others are just the same. So TCP is the worst, except for all the others, I think, is like the summary. And you just have to design your system to work with the internet rather than against it, and understanding how. So if the context here is I'm trying to help people design a distributed system that works on the internet scale, and so 300 millisecond links is something you simply have to deal with. Whereas if you're dealing with like stuff within a data center, it's like hard. It doesn't it's fine. It's like, but it's when these round trips get really long, then it turns out you're completely latency bound and not bandwidth bound at all. Actually, let me show you the second example. I think the difference between these two, if I remember correctly, is that the one at the bottom has a bandwidth on all of those links, which is 10 times higher than the bandwidth of the top one. However, what you will see is that the amount of time it takes for all the messages to get from one end to the other is not that much different, despite the factor of 10 difference in the bandwidth. So the latency is the same, but the bandwidth was 10 times bigger. And yes, it is quicker, but it's not like 10 times quicker. The point is latency in these kinds of things really matters, and the traffic pattern really matters. And this makes it relatively easy to see that and to illustrate that point to people who don't really want to believe it. That is all.
Okay, yeah, let's leave it here.
Thank you, Duncan and Armando.
Okay.